Hello everyone. Welcome back to Foolish Engineer. We have seen basics about BMS some 5 years ago, and after mastering this topic, we have decided to go more deeper into this. First, let's have a quick recap about the BMS. BMS's most important job is to take care of battery by keeping it safe and healthy at all times. To do that, BMS has multiple blocks which take care of different systems, which are cutoff switches, cell charge and voltage monitoring, communication, cell balancing, temperature monitoring, a real-time clock, onboard microcontroller unit, current sensor, and different type of protections. We are zooming some more into these modules one by creating a video series on battery management system. Today, we're diving deeper into one of the core functions of a BMS, which is current sensing, especially in low voltage battery management systems. If you're building, debugging, or just nerding out on BMS design, you're in the right place. So stick around till the end. If you ever felt stuck between your circuit ideas and an actual working PCB, then let me introduce our partner of today's video, which is Altium. Altium Designer is a complete PCB design tool where we capture schematic, design PCB layout, run simulations, and create manufacturing-ready electronic circuit all in one software. It starts with schematic capture, where we transform our paper circuit to a proper design, which is ready for simulation and layout. Then we can run SPICE simulations to test our design, to check the performance and catch any mistakes before they cost us time and money. And after that, we can directly optimize component placement on PCB and design layout with advanced routing tools. It even helps with wiring harness design, where we can plan, design, and document our wiring harness, which connect PCBs with each other. And now it gets even better with Altium 365, which connects our design to our teams, manufacturer, and even component suppliers through cloud. With this, our team can review, comment, and collaborate on the projects from anywhere in the world. Very important feature is its BOM portal. It keeps our component sourcing organized, where we can track component availability, compare suppliers, and check if we got the right parts before placing an order. So remember, Altium Designer is where we design our electronics, and Altium 365 is how we connect with the team to build the project into reality. And the best part is you can try Altium Designer for free, and when you buy the license, you get 25% discount. Just have to click the link pasted below in the description. So, now on the video. Well, first question we need to ask is, what is this current sensing and why BMS needs it? Current sensing simply means measuring the amount of electric current going in or out of a battery pack. In other words, it's all about tracking the flow of charge. If we think about our mobile banking app, every time money comes in, it's recorded as a deposit. Every time you spend, it's recorded as a withdrawal. In the same way, a battery management system uses current sensing to monitor electrical charge entering and leaving the battery. It's like a real-time transaction log, but for electrons. So what does the BMS actually do with that information? First, it tells us how much charge is remaining in the battery, which is the state of charge. Second, it helps keep an eye on the battery's long-term health. Over time, all batteries degrade. By monitoring current, the BMS estimates the state of health also. Third, and most important, it's about safety. Imagine you're charging your battery and there's a sudden spike in current. Things heat up. If left unchecked, it could cause the battery to swell, smoke, or even catch fire. BMS disconnects the circuit by sensing the current when things get dangerous. Now the question is, how does the BMS actually measure current? There are two common ways: shunt-based sensing and Hall effect sensing. Let's break them down one by one. In shunt-based sensing, a tiny resistor called a shunt resistor, is placed in series with the battery or load. When current flows through it, it causes a small voltage drop across the resistor. By measuring this voltage and applying Ohm's law, we can calculate the current. We don't want to waste much energy as heat, so the shunt resistor value should be very small, typically between 1 to 5 milliamps or even lower if currents are higher. Of course, the trade-off needs to be about the resolution of current sensing via ADC channels. As lower the current shunt resistors, lower is the voltage that needs to be measured that requires a sensitive sensing resolution. The best combination shall be the resistor value which minimizes power loss while still providing a measurable voltage. But here's the thing, still the voltage drop is usually very small, in the millivolt range directly at the resistor. So we need to amplify it. That's where a current sense amplifier comes in. It boosts the small voltage signal so it can be read accurately by a microcontroller or an analog to digital converter. And that's how we know the current. We have seen different types of current sense amplifiers in our op-amp series. You can click here to watch those. Now let's look at the second method, Hall effect, also called as magnetic current sensing. You may have seen a clamp meter that measures current without directly touching the wire. That tool is based on the same Hall effect principle. When current flows through a wire, it generates a magnetic field around it. A Hall effect sensor is a tiny transducer that can detect magnetic fields and convert them into electrical signals. If you place a Hall effect sensor near or around a current carrying conductor, the sensor will pick up the magnetic field produced by the current and generate a voltage output proportional to the field strength. Because the strength of the magnetic field is directly related to the current flowing in the wire, the sensor's output voltage is directly proportional to that current, so it can measure the current indirectly with no direct electrical contact. This technique allows for non-intrusive, electrically isolated current measurement. Now comparing shunt and Hall sensing. Both of these approaches are widely used in battery management system, but each comes with its own trade-offs. Let's compare them across key metrics. First is accuracy. When we talk about accuracy, the current sensing precision can make all the difference. Shunt-based sensing offers excellent accuracy. Because it measures a voltage drop across a known resistor, so it gives a highly linear and precise reading. That's why it's the preferred method in applications where exact current measurement is critical, like estimating state of charge or Coulomb counting. Hall effect sensors, on the other hand, are generally less accurate, especially at lower currents. They're more sensitive to temperature changes, sensor drift, and external magnetic fields. Still, they're accurate enough to detect high current levels, short circuits, and fault conditions, or for general monitoring. Next up is power loss. One drawback of shunt-based sensing is power loss. Even though the shunt resistor is tiny, it is still in the path of the main current. At high current, it can generate heat and waste power. Hall effect sensors avoid this completely. Since the sensor doesn't touch the current path, there's zero insertion loss, which means no wasted power due to the sensor itself. Now let's look at isolation. Hall effect sensors inherently provide electrical isolation between the sensed current and the sensor output. This is extremely useful in noisy environments or when sensing on the high voltage side of a battery system. Shunt sensors, on the other hand, do not provide isolation by default. In low voltage systems, this usually isn't a problem. But in high voltage or safety critical systems, extra isolation components might be needed if we're using a shunt. And now, let's look at complexity and cost. Shunt-based sensing is cheaper and simpler to implement. You just need a precision resistor and a good amplifier, both of which are cheap and easy to integrate into a PCB design. Hall effect sensors are usually more expensive and more complex. They might also require calibration or magnetic shielding depending on the surrounding environment. And finally, the size and integration. Shunt-based sensing is compact and can be easily integrated into tight PCB layouts. This makes it ideal for space-constrained designs like power banks and small electronics devices. Hall effect sensors, especially the ones used for high current, tend to be a bit bulky. Also, these sensors often need to be placed carefully around the current path to get accurate readings. So, where is each method used? If your application needs high precision, low cost, and doesn't need isolation, such as in laptops, power banks, and solar inverters, shunt sensing is your best bet. But if your system needs electrical isolation, non-intrusive measurement, or operates in a noisy environment, then Hall effect sensing makes more sense. They're used in industrial machines, electric vehicles where the current can be very high, and safety or electrical isolation is a must. So which one is used in low voltage BMS? You guessed it right. A shunt-based sensing is more reliable for low current, especially less than 100 amperes, and low voltage BMS less than 100 volts. Why? Because in systems like 12 volts, 24 volts, or 48 volts battery packs, isolation is not needed, but cost and accuracy matter a lot more. That's why we find shunt resistors in everything from laptops and electric scooters to home inverters. Hall effect sensors are great when we want to handle very high current, like 1000 amperes or more. High side versus low side shunt sensing. Now, there's one important design decision we have to make when using a shunt-based current sensor, which is where should we place the shunt? There are two common options, low side sensing and high side sensing. Let's start with low side sensing. In this setup, the shunt resistor is placed in the return path, typically between the load and ground. It makes the current sense amplifier operate at a common mode voltage close to zero, which is easy to work with. Most op-amps and ADCs are designed to handle ground-referenced signals. That's why this setup is simple, cost-effective, and used in many BMS ICs, especially in battery packs ranging from 12 to 48 volts. Also, since one end of the shunt is grounded, there's no need for electrical isolation. It is less complex and cheap. But of course, it's not perfect. Here's the catch: any noise or voltage drop in the ground return path can affect the accuracy of the current measurement. Since most of the time the sensor is active when current is flowing, and a current flow in resistors still introduces slight ground voltage shift, which affects the communication ground. Now let's talk about high side sensing. Here, the shunt is placed between the positive terminal of the battery and the load. The big advantage here, there is no ground shift due to shunt voltage drop, which eventually maintains a rigid ground connection for the communication devices. But it does bring in a design challenge. We need an amplifier that can handle a common mode voltage equal to the battery voltage. And most often such op-amps are costlier and prone to introduce unwanted errors. In high voltage systems, this becomes more tricky. We can use some easy tricks like this, which we saw in this video, where we can easily measure high voltage current. So how do we decide? If we want a simple analog front-end design, low side sensing is a great choice. Since everything is referenced to ground, we can use standard op-amps and ADCs without worrying about complex circuitry or high voltage common mode issues. It's simple, cost-effective, and gets the job done for most low voltage systems. But if we're dealing with critical systems that must maintain a rigid ground, then high side sensing is a better fit. It keeps the rest of your system stable, even if something goes wrong. However, in 12 volts and 48 volts, battery systems, both high side and low side sensing are used. At the end of the day, the choice depends on your BMS architecture and the ease of PCB layout routing simplicity. I hope this gave you a clear picture of how current sensing works in BMS, especially for low voltage systems. If you learned something from this, don't forget to check the description for references. If you found this video useful, hit that subscribe button and stay tuned for more exciting content.